Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. The learning objectives for this module are to understand how virtual memory is implemented in Windows NT and to learn how virtual memory is implemented in Solaris 2 and to understand certain other considerations that are required for paging. So, first we will learn how virtual memory is implemented in Windows NT. In Windows NT, demand paging is used along with a method called clustering. So, what is clustering? Multiple pages surrounding the faulting page are also brought into the main memory. Whenever there is a page fault, usually what we do is that we bring in the page only for which a page fault had occurred, or only the required page is brought in from the secondary storage device into the main memory. But here what is done is that in clustering, you look at the pages, maybe the pages that are before this particular page for which there was a fault, and also the pages that are after this particular page, and bring in that set of pages or the cluster of pages into the main memory. So, what is the advantage of this? Suppose you have a page fault for page number 10, and immediately if the memory reference is to the next page, that is page number 11, then there will not be a page fault, because when there was a page fault for page number 10, you would have brought inside page number 11 as well. And hence, whenever there is a memory reference to page 11, there is no page fault and it is present in main memory itself. And the next thing what is done in this Windows NT is that whenever a process is created, that process is assigned with two values, that is a working set maximum value and working set minimum value. What is meant by a working set? The working set is the set of active pages for that particular process at that particular time, and these many number of pages is allocated for that particular process in the physical memory. Say the working set minimum is say some 10 and the working set maximum is say some 20. So, working set minimum is the minimum number of pages the process will certainly have in memory. So, that process will be assigned at least 10 physical frames in the physical memory. And working set maximum is the maximum number of pages that process can have in physical memory. So, if working set maximum is 20, then it means that the process will be assigned a maximum of 20 physical frames in the physical memory. But at some times this 20 can be exceeded, a few more physical frames can also be given to this particular process. And there is another entity or a process called a virtual memory manager in Windows NT. What does this virtual memory manager do? It maintains a list of free page frames. So, whichever page frames are free, those frames will be maintained or will be remembered by the virtual memory manager. And now, if the number of pages for a particular process goes below working set maximum, as I told you in the example, say 20 is the maximum number of pages that can be assigned to a process, and if that particular process has got less than 20 physical frames in the physical memory, and now if a page fault occurs for that process, this virtual memory manager will allocate a free page from the list of free page frames for this process, because this process can have a maximum of 20 physical frames, but it has got currently only less than 20 physical frames. So, it can assign one more frame, one more free frame for this process when the page fault occurs. But when the number of pages for the process is currently at the working set maximum, or say in this example, if the process has got exactly 20 physical frames now, and now if there is a page fault, we do not assign a new free frame for that process. What is done? Whenever a page fault occurs, a page is selected for replacement, or one of the 20 frames or one of the 20 pages that are currently in physical memory for this process is selected as the victim page, that is moved out and the required page is brought into the physical memory. That is, local replacement is done. One of the pages that are allocated to the process is moved out and the required page is brought inside. And a threshold value is also associated with the list of free page frames. So, there is a virtual memory manager who is looking at or is taking care or looking after a set of free page frames, and it is necessary that some minimum number of free page frames is always maintained. So, a threshold value is kept for that. So, when the number of free page frames goes below this threshold value, a procedure called the automatic working set trimming is done by the operating system. So, what is done in this automatic working set trimming? If any process has got pages more than its working set minimum, then the manager will remove those pages from that particular process. Why is it is doing so? It needs to maintain some minimum number of free page frames, but that free page frames has gone below this threshold value, at least the minimum value it wants to maintain, it goes below that, and hence what it does, it looks into the processes that are kept in the physical memory. It looks at the pages for those particular processes. It checks if the working set, if the pages allocated to those particular process are more than the minimum number of pages that can be allocated to that process. If it is more than the minimum number of pages, it will remove those pages from that particular process and put it into the list of free frames. And if sufficient free pages are available, say you have more than the threshold value, more free frames than the threshold value, and then it is possible to give the processes in the physical memory or a few more pages. So, the process with the minimum number of pages can be given now more number of pages. So, that is how virtual memory is managed in case of Windows NT. Now, we will see what happens in the case of Solaris 2. In Solaris 2 operating system, a list of free pages is maintained, very similar to how a list of free pages is maintained in Windows NT. And whenever there is a page fault in Solaris 2, a page is assigned from the list of free frames. And there are a few parameters that are being maintained in the case of Solaris 2. So, one is a threshold called the lots free, and this is associated with the list of free pages. So, what is this threshold value? It is approximately equal to 1/64 of the size of the physical memory. And what is the use of this threshold value or this threshold parameter? The kernel will check frequently. Actually, it does this checking once 4 times per second, and 4 times per second the kernel will check if the free memory that is available or if the free pages that are available is less than lots free or this value of this parameter. When the number of free pages is below this lots free, it goes below the threshold. Now, it starts a procedure called the page out procedure, and this procedure is very similar to the algorithm that you had seen earlier, and it is called the 200 clock algorithm. It is similar to the clock algo that you had seen earlier, and this clock 200 clock algo, what happens is you have a first hand of clock that will scan all the pages in the memory, and it will check the reference bit of all the pages in memory, and all the reference bit will be set to 0. And then you have the second hand of the clock or the second iteration, in which it will scan all the pages again the second time, and if the reference bit is still 0 or if the page has not been referred to the second time, then that page is added to the free list. So, the set of or the number of free pages is going below some value, some minimum, some value called the lots free value, then it needs to add more pages to the set of free pages. So, for that it does this second chance algorithm or this two-handed clock algorithm. And the rate at which pages are scanned or pages are checked here is done at a particular rate called the scan rate, and the scan rate is measured in pages per second. And the scan rate, the rate at which the scanning is done, can also vary from a particular value to another value. So, the minimum value is slow scan and the maximum value is fast scan. And now, when the free memory is less than lots free, the scanning will start or it will happen at slow scan pages per second, and gradually it will progress to fast scan pages per second. And the default value for slow scan is 100 pages per second, and the default value for fast scan is total physical pages by 2. And the distance between the hands of the clock is determined by a variable or a parameter called hand spread, and this distance is measured in pages. And the time between the front hand clearing the bits, the reference bits, and the back hand checking if the reference bit is set again is determined by the scan rate and the hand spread parameters. Say if the scan rate is 100 pages per second and the hand spread is 1024 pages, then you can see that there will be 10 seconds between the front hand and the back hand, because you have a scan rate which is happening at 100 pages per second. So, in the first second it will scan 100 pages, in the second it will scan the next 100 pages. So, in 10 seconds it will scan nearly 1000 pages. So, the time or the number of pages that happens between the front hand and the back hand is 1024 pages, and hence it will take around 10 seconds for that to happen. And now, if the free memory falls below another parameter called des free, this des free is a value which is even less than lots free. So, when it was less than lots free, page out will run at a rate which is less than this 100 times per second, but now when the free memory falls less than des free, which is much less than lots free, the page out happens in a much faster rate. It happens at 100 times per second. And if the free memory falls below des free, page out runs at 100 times per second, and if page out is unable to keep this free frames at least at des free, then what is done is processes are swapped out. So, processes which are idle for long periods of time are chosen and those processes are swapped out. And if the free memory now falls below min free, that is which is a value, min free has got a value which is even less than des free, then page out is called for each and every request of a new page. So, depending on how many number of free frames are available, Solaris 2 acts accordingly. It has got 3 parameters: lots free, des free and min free. If it is lots free, scanning will happen at 4 times per second. If it is des free, scanning will happen at 100 times per second, and if it is less than min free, page out will happen for each and every request for a new page. So, that is how virtual memory is implemented in Solaris 2. Now, we will learn certain other issues that are related to this page replacement and allocation of frames, certain other considerations which the OS has to consider, so that you can optimize the performance of the operating system. One is called this PrePaging. So, whenever a process initially starts executing, there will be a large number of page faults. That is because you may have to bring initially the locality into the memory. So, it is pure demand paging. Initially no page of that process is kept in the memory. So, each and every reference to the pages in that particular locality will result in a page fault. Say if there are 5 pages in a particular locality, then you need to bring in all the 5 pages so that the locality is brought in, and after that maybe when you are executing that in that locality there will be no page fault. So, initially there will be a lot of page faults. And there is another situation where a lot of page faults can happen, is that when you have swapped out a process and then you are trying to swap in the process and you are trying to restart that process, then all the pages of that process have to be brought into memory, and hence you will have a lot of page faults there also. So, rather than doing this, rather than bringing one page at a time and servicing the page faults, what is done here is that you do something called pre-paging, in which you bring into memory at one time all the pages that will be needed. So, here you need to look at the list of pages that are kept in the, that are present in the working set, or what is working set? The set of active pages now, and then you need to bring in all those pages inside. So, whenever say you need to resume a process after having swapped out, then you need to bring in the entire working set. So, what is done whenever you are swapping out the process, you also remember which all pages or how many pages were present in the working set, and that many number of pages or all those pages in the working set are brought into the physical memory, and in one stroke it is brought in. So, this is called pre-paging. But is the cost of pre-paging less than the cost of servicing page faults? What you need to look at is that when you are trying to service page faults, for each page fault you need to look at select which process, which page has to be brought in, you need to interrupt, then the interrupt has to be serviced, then IO has to happen to bring in the page, and the process may have to wait for IO, waiting in the disk queue and so on. So, all this is lot of overhead, and many pages brought into the memory may not be used. That is another thing that you need to consider when you are looking at pre-paging. Say at one stroke if you are trying to bring in all the pages, will all these pages be used? Certainly we do not know. So, this depends on pre-paging, or the advantage of pre-paging depends on how much of the pages are actually being used. If most of the pages that are brought into the memory are used, then pre-paging is advantageous. So, the next issue is to look at the size of the page. So, how do we select a page size? Page sizes generally vary from 2 power 12 to 2 power 22 bytes, and different issues that you need to look at to decide upon the size of the page are there are different issues for that. One is the size of the page table. If you decrease the size of the page, then the number of pages will get increased. You decrease the size of the page and you will divide the process into small pieces, and hence you will have lot of pages. When you have a lot of pages, the number of entries in the page table will increase, and because of this the size of the page table will increase, and each process will have its own page table, and then you will have lot of page tables with so much of space requirement. So, in that case what is advantageous is that it is better to have a larger page size. When the page size is larger, you have less number of pages, and hence you have less number of entries in the page table, and because of that the size of the page tables become small. But the disadvantage in this case is that when the page size becomes very large, then in the last page, most of the page, if it's not, most of the contents are not occupied, then the space gets wasted, and that leads to internal fragmentation. And the second issue is that to think about page size is that the time required to read or write a page. What happens if the page size is large and if you need to read that page from the secondary storage device? And you know that IO time comprises of seek time, latency and transfer times, and transfer time is proportional to the amount that is transferred. So, if the size of the page is large, then you need more time to transfer that particular page. Smaller page size will require less amount of I/O. And the total I/O is also reduced because locality is improved with smaller page size. When you have a smaller page size, most of whatever you want to read will be within that particular page, and you may not try to bring in a big page size and some of the contents which are not being used at all. So, smaller page size will more accurately match the program locality. So, it is preferred to have a smaller page size when you are looking at I/O. And the next issue that you need to look at is the number of page faults. If the page size is very small, then you will have more number of page faults. Say suppose the page size is only 1 byte, then you may have a page fault for each and every byte, and gradually if you try to increase the size of the page, then gradually the page faults also will get reduced. So, to minimize the page faults, the number of page faults, it is better to have a larger page size. And as we all know, a page fault generates a large amount of overhead. But we see that in recent times, in recent architectures and in recent operating systems, larger page sizes are being used. And the next issue that need to look at is called TLB Reach. We have already learnt about a parameter or a metric called the hit ratio. What is hit ratio? It is the percentage of virtual address translations that are resolved in the TLB rather than looking at the page table. So, you get a lot of TLB hits if you get a lot of entries in the TLB itself, page table entries in the TLB itself, then they are hits. Now, if the TLB is larger in size, then you have more entries in the TLB and hence the hit ratio is better. Now, what is TLB reach? That is the amount of memory that can be accessible because of looking into the TLB. So, that is nothing but the number of entries in the TLB multiplied by the size of a page. So, if you have 5 entries and if each page is 1 KB, then you can access 5 KB of memory using the entries in the TLB. So, that is called that 5 KB is called the TLB reach. So, ideally if you have the working set for a process stored in the TLB, then you can access memory very easily by just looking into the TLB. Else there will be a lot of misses and more time will be taken to access a particular page. So, increasing the number of entries in the TLB will increase the TLB reach. And another way in which you can increase the TLB reach is that you can increase the size of pages. So, when you increase the size of pages, the number of page table entries will become small or the number of pages will become small. So, you can have more number of information about pages kept in the TLB. So, you can have a better TLB reach. Say for example, you can increase the size from 8 KB to 32 KB, and because of that, if you increase the size of the pages from 8 KB to 32 KB, the number of pages will decrease 4 times, and hence the TLB reach will increase 4 times. But the problem again is that when the size of the page is much larger, it will lead to internal fragmentation. And in certain operating systems, what is done is that different page sizes are being used so that you can increase the TLB reach. So, in Solaris, you have 2 different page sizes, one is 8 kilobyte and the other is 4 megabyte. So, for kernel code and kernel data, they are using 4 megabyte size, and they have 2 4 MB pages, and for most of the applications they are using 8 KB pages. So, it is also possible to have different varied sizes for the pages rather than having a fixed size for a page, so that you can improve the performance. And the next issue that you need to look at is that, say if the user is writing a program and if the user has got an awareness of the underlying demand paging, then it can improve the system's performance. Now, look at this program in which they declare an array which is of size 128 comma 128. The size of the array is 128. Suppose the size of a page is 128 byte, and how are arrays stored in the physical memory? Each row will be stored first and only then the next row will be stored. So, here it is an 128 by 128 byte array, and the size of the page is 128 bytes, and hence the first row of the array will be stored in the first page, the second row will be stored in the second page, etc. and so on. So, totally you need 128 pages to store this entire array. Now, if you write a program like this, where say for j is equal to 0, j less than 28, j plus plus, for I equal to 0, I less than 28, I plus plus, the outer loop has got the j index and the inner loop has got the I index. So, the first element referred to here will be data of 0, comma 0. The second element will be j will be 0, I will be 1. So, data of 1, comma 0 and so on. So, it will be data of 0, comma 0, data of 1, comma 0, data of 2, comma 0 and so on. That is, it will be referring to the first element in each of the rows. So, the first element in the first row, then the first element in the second row, the first element in the third row and so on. So, because of this, what happens for the first assignment, it will try to locate the first page. For the second assignment, it is the second row, the first element in the second row, and hence it will try to locate the second page. For the third assignment, it will try to locate the third page and so on. So, for the first set or the first inner loop for I equal to 0 to 128 or 0 to 127, it will try to locate all the 128 pages. And then again for the next value of j, when j equal to 1, it will again try to have a memory reference for all the 128 pages. So, totally there will be 128 by 128, 16,384 page faults. But if the program is written in this manner, say you write I equal to 0 to 128 and j equal to 0 to j less than 128, data of I comma j equal to 0. The first element will be 0 comma 1. The second element that you can look at here will be 0 comma first element will be 0 comma 0. The second element will be 0 comma 1. Third will be 0 comma 2, etc. and so on. So, in sequence they try to access all the elements in one particular row. So, all elements in one row will be accessed, and only then all elements will be second row will be accessed and so on. So, because of that, all elements in the first page will be accessed, and then all elements will be the second page will be accessed and so on. So, you get only 128 page faults. So, if the user also has got some idea about how demand paging works, then he can write a better program, and because of which he can reduce the page faults, and because of this the performance can be improved. So, summarizing what we have seen in this module, we first understood how virtual memory is implemented in Windows NT, and then we learned how virtual memory is implemented in Solaris 2. Then we learnt about pre-paging, where you try to bring in a set of pages into the main memory rather than bringing only the page that is required. Then we saw how page sizes can be. Can it be large or can it be small? What are the implications of having different sizes of pages? And then we understood what is meant by TLB reach, how much amount of memory can be accessed by just looking into the contents of the TLB. Then we also saw how program structure will affect the performance or will affect the number of page faults, and the user having knowledge about this program structure and the demand paging will lead to better performance. References. Thank you.